Hi everybody, Dr. Burns here. Let's take a look at section 2.3, which is on solving differential equations that are known as linear equations. So this is a new topic. I don't think this is something you would have seen in any of your prior classes. So make sure you have your cell phones put away and turned off so you can really focus and take some good notes for the next 10 minutes or so. First of all, I want to remind you of what we mean by a linear differential equation. So a linear differential equation, and remember we're only looking at first order differential equations, so that means just the first derivative in this chapter, but a linear differential equation is going to be in the format like this, where you've got dy dx, and then you've got some function of x times y. So the y, or the dependent variable, is just raised to the first power. If it has anything in front of it, it would be considered a function of x equals some other function of x. And this is considered the standard form of a linear differential equation. It does not have to start out in this form, obviously, to be a linear equation, but you have to be able to get it in this form where this dependent variable is just raised to the first power, and that's it. So let's go through just a couple practice questions to decide if each of these are linear or nonlinear, and if they are linear, if they are separable or not. So let's try the first one. We've got x squared sine x minus cosine xy equals sine x dy dx. And if you're not sure, you can try to algebraically manipulate it to see if you can get it in this format. So I would probably leave the dy dx term where it is and move the term that contains the y to the other side. So that would give me x squared sine x equals sine x times dy dx. So y is the dependent variable plus cosine of x times y. And I'm hoping you can see that this y, that's what makes it linear. If you need to do one more step, you can divide everything through by sine x, and you'll end up with x squared equals dy dx plus cosine x over sine x. You can, of course, rewrite that as cotangent if you wish, times y. And so there's the linear term that you need. So yes, this is linear. Is this separable? That's a little trickier to answer. I would say look at it. And I don't think there's a way to do it because of that plus sign. Generally, to be separable, you're not going to have multiple terms with addition or subtraction. So I'm going to say not separable. So we'll come back to what to do in just a few minutes. But the main thing I want you to understand is that it's not linear. Let's go ahead and look at example B. We can move some things around and do some algebra here. I could maybe even divide everything through by y to get the dy dx by itself. But regardless, what I want you to notice is that this term right here is y cubed. Even if I divide by y, it's going to be y squared. I'll have a y on the other side. The other side has to just be a function of x. So this is definitely not linear. So you don't have to worry about that. And I don't believe this is separable. You could do some algebra here, and I think you'll see that this also is not separable. You're not going to be able to separate these variables. How about letter C? We've got dx dt. So x is now the dependent variable, so just kind of keep that in mind. Dx dt equals xt. So x is that dependent variable. So there it is. That's the dependent variable as a linear term. T is now the function of t, where it says q of x and p of x. Don't get confused. That's really now a function of t in this equation. Equals e to the x. And I would say this is a no as well. And the reason, it looks like maybe at first glance it's going to work out, but the problem is, remember, x is the dependent variable. So this e to the x doesn't cut it. In order for this to be linear, this would need to be a function of t, because t is the independent variable. So this q of x, remember, that's in terms of the independent variable. So because this is in terms of the dependent variable now, that does not work. Is this separable? I'm trying to think if we could maybe, I don't think it is because of that plus sign, so I'm not going to worry about that right now. Let's try letter D. We've got 3t equals e to the t dy dt plus y times ln of t. So first of all, make sure you establish y is now the dependent variable, t is the independent variable. There's the dependent variable, the linear term that I need, times a function of the independent variable, which is t. So I think we're okay here. If I divide everything by e of t just to get it into standard form, I would wind up with dy dt plus natural log of t over e to the t times y equals 3t over e to the t. So there, I've got my linear term. Let me scroll back up a little bit. I've got my linear term. I've got a function of t right here, and then I've got another function of t right here. So I would say yes. However, this is definitely not separable. I'm trying to think, and I don't think there's any way to make this separable. All right, so again, not separable. I don't think any of these actually are separable, but that's okay. All right, don't worry, we'll talk about what to do in just a moment with that part of it. I just want to make sure we're clear on what's a linear equation. How about the next one? We've got 3r equals dr d theta minus theta to the third. So establish in your mind, r is the dependent variable, theta is the independent variable. So I think we are good to go here. If we want to put this in standard form, you'll see that we have dr d theta minus 3r equals theta to the third, just moving some things around here. There's my r is the linear term that I need, and I've got a function in terms of theta on the right side and in front of the r. So yes, this one is linear, but again, not separable because that minus theta cubed. I think that's going to mess us up. All right, so let's talk about what to do if it's not separable, but we have a linear differential equation. So one option is to use what's called the integrating factor method. And here's the technique. First, make sure that your differential equation is in standard form, so dy dx plus p of xy equals q of x. Then you're going to find what's called the integrating factor, hence the name. We call that mu of x, and that's equal to e to the integral of p of x dx. That's why it's important to get it into standard form, so you can clearly identify what p of x is. Then you're going to multiply both sides by mu of x, and then you should be at a position where you can integrate it. And I put a little note here, look to reverse, quote unquote, the product rule. So let me give you an example and show you what I mean. So first, look at example 2, and I want to just preface all of this by saying your best bet is to always look to see if the differential equation is separable, because if you can separate the variables, that's your best route. So to do that first, that's the most straightforward method of solving it. In this case, this is not separable because of that minus 2yx squared. So what I am going to do is see if it is linear, first of all. And I'm going to try writing it in standard form. So I need to get rid of this 1 over x term. That means this would become dy dx equals, I'm going to multiply everything through by x in this case to do that. So I get dy dx dy dx minus, if you multiply the second term by x, that becomes 2 over xy equals x squared cosine x. So that certainly is linear. I've got my linear y term there. I've got a function p of x in front of it. And then I've got my q of x function on the other side. So then the next step is to find the integrating factor. So the integrating factor, mu of x, or just mu if you want, is equal to e to the integral of p of x. So in this case, I hope we see p of x is negative 2 over x. That's the function in front of the y. So I'm going to do e to the integral of negative 2 over x dx. So the negative 2 can move to the front because that's a constant multiple. So I just have 1 over x dx, which is the natural log. So I've got e to the negative 2 natural log of x. You do not need to worry about the plus c. That'll wash out in the end when we do the final level of integration. So you don't need to worry about that. What I do want you to notice, though, is that you've got e and a natural log. Remember with log properties, remember the power rule with logs. If you have p times the natural log of x, you can write that as natural log of x to the p power. So if we do that here, this expression becomes e to the natural log of x to the negative second. And remember, this is a really important property. E to the natural log of x is just x. So if I have e to the natural log of x to the negative second, that just simplifies to x to the negative second. And that's what you're going to use for your integrating factor. So we're going to multiply both sides of the equation by that x to the negative second. I'm going to use a different color here just so it stands out. So my equation now becomes x to the negative second times dy dx. And then we've got, let's do minus x to the negative second again times 2 over xy. And then equals, on the other side, we're going to have x to the negative second times, and I'm just going to do a big parentheses for now on the other side, x squared cosine x. All right, now let's simplify this just a little bit before we proceed and see what we're looking at here. First term, nothing changes. The second term, this becomes, so let me rewrite it. We have x to the negative second dy dx, and then this becomes minus 2x to the negative third times y equals, and if I multiply those together, I just have a cosine x on the other side. Those two coefficients will cancel each other out. Now, here's the thing that's a little different that I want you to notice. When I said back here, look to reverse the product rule. This is the sort of the format it's going to follow every time when you use this integrating factor method. This is the derivative of the product of two expressions or two terms. This dy dx would be the derivative of y, and negative 2x to the negative third would be the derivative of x squared. So this expression, this is d dx of y times x to the negative second. Pause the video if you need to and make sure you see that. Take the derivative of this using implicit differentiation with respect to x, and you'll see that you get this expression. So when I say this is sort of the reverse of the product rule. So now I've got the derivative of y x to the negative second equals cosine of x dx. And then if I integrate both sides, well, don't overthink the left side here. What is the integral of the derivative? It would just be the integrand itself. So this becomes y x to the negative second equals, integral of cosine would be sine x. And remember, we said to just put your plus c on the side with the independent variable. And then if you can easily solve for an explicit solution, go ahead and do that. I'm going to divide both sides by x to the negative second here. And I end up with y equals, I'm going to move the x to the negative second to the top, so it becomes x squared sine x plus cx squared, or you could just put the x squared in the front, but that would be the general solution to the original differential equation that they gave us. And that is the integrating factor method. We will do plenty of practice with this tomorrow in class. So be sure you're there, bring your notes, and I'll see you then.